Hi there, guys. Well, we're about to do inverse functions, building up to exercise 2N in the book. It's mostly inverse functions. There's just a few definitions here as well. There's a definition for an identity function. There's obviously the definition for an inverse function, and there's self-inverse functions as well. Now, obviously, a lot of people will have done this stuff before. Just some of these questions, again, are extended by looking at the domain and range of inverse functions and so on. Okay, so these questions do get more complicated. Okay, well, let's just start off with this definition, which I've just copied over here. And first of all, it talks about the identity function. So the definition for this is to say, well, if we have two functions, then the identity function here, there you go, 1 second, the identity function f is that when composed with g leaves g unchanged. So, for example, f of g of x is the same as g of f of x gives us this answer of g of x. So in the case of functions, there's really not much to think about here. And this is not a particularly interesting question, and you would be very unlikely to be asked about this, but we're talking about the identity function for functions being y equals x. So what are we talking about? Here's f of x. In other words, y is equal to x here. And if we combine these things here, if we do f of g of x, or if we do g of f of x, that's either putting g of x into f. So whatever g of x is, you put that in where we normally see x. And so that's just going to change to 3x minus 2. And obviously, this is pretty straightforward to do as well. Putting in f of x, which is x, into g of x, and it's just going to give us the same thing, of course. So we're getting g of x in both of those cases. So f is not changing it. Right, okay, so the identity function is f of x is equal to x, or y equals x. Now, what we're really talking about here is building up the system of functions and our understanding of the algebra of functions, if you like. So, for example, in multiplication, we have an identity operation. If we times 5 by 1, we get 5. If we times 100 by 1, we get 100. So that's the identity operation in this case. Likewise, with matrices, you'll have 1, 0, 0, 1. That's the identity matrix. That's going to leave any x, y matrix as x, y. So identities exist in lots of systems in mathematics. Okay, and so that's what we're building up from here. Okay, well, you could probably have skipped that, to be honest, but there you go. We're having a complete understanding here. So, right, let's take the next bit then. Inverse of a function. Okay, so let's just take this, okay? So the inverse of a function is defined. So a function h, when composed with g, results in the identity function. Right, so basically, if we have f of x is some function, then when we do f to the minus 1 of that thing, we take the answer back to x. So, for example, if f of x is x squared, then f to the minus 1 could be the square root, and that takes us back to the original function. Okay, we might need to define that for x is greater than 0, but greater than or equal to 0, but you get the picture, right? The inverse function of f of x being x squared is going to be f of x is equal to the square root of x. And again, as I said, we might need to say there that this is actually defined for just x is greater than or equal to 0. Okay, so yeah, perhaps x squared was not the best choice. Let's think of another one. If we're talking about x plus 3 is the function, then you can quite obviously see that f to the minus 1 of x is equal to x minus 3. So let's do a test case here. If I did f of 5, that gives me the answer of 8. And now if I do f to the minus 1 of 8, that brings me back down to 5. Now that's just showing it, of course, but we can also show the whole thing algebraically here by saying f to the minus 1 of f of x. Okay, so put this inside here, and we're getting x plus 3, and then minus brings us back to x. And likewise, if we did it the other way around, if we say f of minus 1 of x, that's also going to give us x as well. Okay, now inverse functions really aren't that complicated if you're talking about just kind of steps. So like straightforward steps, like for linear equations. So a lot of these you can just think about. So just a little example, I said here, if f of x is equal to 2x plus 3, well, the inverse of that is to take away the 3 and divide by 2. It's the undoing function. How do you undo timesing by 2 and then adding 3? Well, you take away 3 and then you divide by 2. Okay, so that's just your normal solving of linear equations, if you like. Now, you will see in this case, just to discuss this, we're saying if we let's just take this screen, okay, just capture that one. So, for example, if we put 1 into our original function, we can see that we get out 5. And then if we put 5 into our inverse function, we can see we get back to 1. But that blue line is essentially the reflection of this red line. Because what we're doing is we're swapping the x and the y around. Really, we're saying, well, if we put in 1, we get out 5. But then the backwards function, or in other words, the inverse function, is saying, well, let's put 5 in and get out 1. It's just the backwards function. But we're essentially switching the axes around. So the 5, 1 is now becoming, the 1 comma 5 is now becoming 5 comma 1. Okay, so all of your x, y coordinate points are now changing into y, x coordinate points, if you like. So, for example, 1, 5 is now becoming 5, 1. Right, and that's the reason or the logic behind the technique which I'm just about to show you on here. But one more thing before we go on to that technique of switching around the x's and the y's. You should also notice that this red line is a reflection of this blue line here. So it's a reflection in the line of y is equal to x. And all inverse functions are a reflection in the line of y is equal to x. Okay, so again, let's just deal with the technique for this one. And the basic technique for doing inverse functions, which a lot of you will know already, is to say, well, look, let's set up y equals 2x plus 3 for this one here. And then let's switch around the x's and the y's. Okay, we're basically switching the axes, which is what I was just explaining. And so we're switching around the coordinate points, and then let's rearrange for y. So let's say x minus 3, and then divide by that 2y, and divide by the 2 plus y. Now, this is your inverse function. So f to the minus 1 of x is x minus 3 over 2. By the way, on Desmos, I couldn't figure out how to do f to the minus 1 of x. It wasn't accepting me to put the power of minus 1 in there, so that's why I called it g of x instead. Okay, well, there we go. So there's the technique. If we let f of x equal to y, switch around your x and the y, and then rearrange to make y the subject, then we can replace y by f to the minus 1 of x. Okay, so that's pretty straightforward. Right, so let's look at the next little bit. So the notation for inverse functions, there we go, is g to the minus 1 of x. We've kind of done that. And yeah, okay, the inverse of a function f taking set A to set B is a relation formed when the domain and range are interchanged. That's what we're up to, and that's what we're coming on to next. So, example 27. So find the inverse of f of x equals x squared plus 3. Now, there's a bit of an issue here already, because we're looking for an inverse function. We've got to realize that this is going to give us a many to one function to start off with. So we have a many to one function. It's going through 3, and it's shifting the x squared graph up by 3. So it's going to look like this. But there are many x's which give us out the same height. So this is a many to one function. Now, when we reflect this in y equals to x, as we discussed a moment ago, we can see that this one is going to look something like this if I'd actually done the axes kind of with the same scale. So this one is going to go like this. That's really not very good. Okay, but you can see I've basically got a different scale on this one. Okay, but it's going to be reflected across here, and that one's 3. Okay, now the problem with the reflection which you're getting out here is that this is now becoming a one-to-many graph. So in fact, it's 2 functions. There's a bit of an issue with this question to start off with, because they really need to state the domain to make it a one-to-one function in order that it has an inverse. Basically, remember that when we're finding the inverse function, we're saying, well, when we're going back from y, where does that come from for x? And if it comes from 2 different places, we have a bit of an issue. Okay, so we're going to end up with 2 functions in that case. That's exactly what's happening here. So we really need to restrict this to either this side or this side. In other words, either to this or to this. Okay, so let's just get rid of that. That's a bit of an issue, and I noticed that that is talked about in a later question, but it's just to say that this question is not great. It's not exam style or exam standard. We find the inverse of this thing here. So let's just do the technique. We've got y equals x squared plus 3. We've got y take away 3. Let's square root that. Let's do steps in 1. And here's our issue. We've got plus or minus there. Which one do we go for? Okay, so that's ambiguous. I think we really should say x is greater than or equal to 0 here. And then for this one, we could go with plus. So we've got f to the minus 1 of x is going to equal to x minus 3. I forgot something, didn't I? I forgot the fact that I didn't change my x's and y's around. This should have been y and this should have been x. Okay, right. So I really should have said x equals y squared plus 3 and then rearrange that one. Okay, so I should have ended up with x minus 3 and square root of this thing here gives us y plus or minus, but in this case we're taking plus. Okay, so now it says justify your answer algebraically. Notice that I've not put a domain on here. I'm just going to come back to that in a second. It says justify your answer algebraically. So the way in which we're going to do that is we're going to say f to the minus 1 of f of x, and we're going to hope that that's going to give us back x. It's going to take us back to the original number. So when we substitute this, f of x into f to the minus 1 of x, we're going to be putting in where we normally see x in f of minus 1 of x, we are substituting in f of x. What is f of x? It's this thing here. So we're going to put in x squared plus 3. Now, those two things are going to cancel, and the square root of x squared takes us back to x. So we're happy about this. This is good. Okay, so we have justified this algebraically. Now, what I was just talking about there, let's just write it in here. Let's just have a look at this on the graph. So a neater graph than the one I was trying to come up with. X squared and then plus 3. So our graph, so you can see it's kind of much deeper than the version that I was trying to draw. And then our inverse function was equal to the square root of x minus 3 here. And so there we go. There's one part of it, and the other part reflected is going to be down there. Now, let's just steal this again so that we can talk about the domain and range. So, okay, so this part here reflects over this line to this part here. So if we're stating that our original function is valid for when x is greater than or equal to 0, in other words, on this side, talking about this bit here, then g of x is valid only from x is beyond 3. So x is greater than or equal to 3. Now you should notice here that the range of this function here, we can say f of x, range, or y, is greater than or equal to 3, which is the same as the domain of the inverse function here. You can probably guess that f the minus 1 of x, which is essentially this g of x, f minus 1 of x. So the range of this is for all values which are greater than 0, which is the same as the domain of the original function. So the range of the inverse function is the same as the domain of the original function, and the range of the original function is the domain of the inverse function. Okay. I mean, that kind of makes more sense if you just said your inverse function is going this way around, because you say, sure, I can only take things which are greater than 3 there, and I can only get out answers which are positive. And that's exactly what we're talking about here. It's because we've made this reflection that it makes it slightly more difficult there. But essentially, the domain and range are flipped around for the inverse function. Okay. Right, let's see what they've done there for this one. Let's see what they've taken. So in the book, they don't discuss the domain and range issues here. So they just take the positive square root and they just verify it algebraically. And so they're happy with it. Okay, right. But we're not happy with it because there are domain and range issues. Right, okay, example 28. Let's have a look at this one. Okay, example 28 says find the inverse of the function here, where x is not equal to 2, and graphically determine whether the inverse is also a function. State the domain and range of the function and its inverse. Okay, so same technique. So let's first of all say, well, we've got y equals 1 over x minus 2 plus 3. And there's this condition, of course, that x is not allowed to be equal to 2, because otherwise you'd have a 0 on your denominator there, which is not allowed. Now let's switch around the x and the y, which is what I forgot to do this time around. Okay, let's take the 3 to the other side. Okay, I mean, these are pretty obvious steps. Let's multiply across by the y minus 2. Let's multiply that out, so we're getting xy minus 3y minus 2x, and we've got minus 6 there. Minus 6, no we haven't, we've got plus 6, and that's equal to 1. Let's take the 6 to the other side, that's minus 5. Let's take the 2x to the other side. So we've got plus 2x and minus 5. And let's factorize out the y, so we've got x minus 3. And you should be familiar with all of these steps. This is stuff that you've done before. And we can divide by the x minus 3. And then, of course, that's equal to your f to the minus 1 of x. So I restate that on the last line, but I'm running out of space here. So I'm just going to say it's the same as this thing here. It's the same as this thing here. Okay. So there we go. There's our inverse function. And out of interest, by the way, I might just put these two together by timesing the top and the bottom. So just put this and this together by multiplying the top and bottom of this by x minus 2. So what have I got? I've got 1 plus 3 lots of x minus 2 all over x minus 2. I'm just combining a couple of algebraic fractions there. And because I'm running out of space, I'm do that all in one, which is a bit naughty. So I'm going to end up with 3x minus 6, and then plus the 1 gives us minus 5, and divide by the x minus 2. Okay, so I've just combined some algebraic fractions there. The reason why I've done that is partly because I can see from this version that we've still got this condition that x doesn't equal to 2. You can see that that's still our denominator. We still can't allow x to equal to 2. But we can also come up with a couple of asymptotes. Your asymptotes for f of x are going to be x is equal to 2, but also if you remember my little trick for finding the y asymptote here, that's going to be, if you take the two highest powers of x, the x and the x will cancel and ignore the other part, and you'll end up getting y is equal to 3. Okay, we did that in a previous video. And then the asymptotes of f to the minus 1 of x, well, you might be able to guess this. Let's have a look at this function. We can see that x is equal to 3 is not allowed to be used in that domain. So x is equal to 3 gives us an asymptote. So we could actually say for this, this is not defined for when x is equal to 3. Okay, and if we take the two highest powers of x there, we can see that x will cancel with x here, and we'll get the asymptote of 2. So y is equal to 2. And you can see, again, just as with the domain and the range being flicked around, also the asymptotes are flicked around as well. So we can see that x is equal to 2 and y is equal to 3 becomes x is equal to 3 and y is equal to 2. Okay, well, that's just a little extra. But it does and graphically determine the inverse is also a function. Well, we'll do that in a second. If you state the domain and range of the function and its inverse, well, we already stated the domain of the original function. It's all of the real numbers and not 2, but the range is not going to include the 3. So we've kind of already said that as well. F of x and not be equal to 3, but otherwise f of x belongs to all the real numbers as well. And you should say f of x belongs to all of the real numbers, comma, f of x does not equal to 3. Okay, and likewise for f to the minus 1 of x, we can say the domain is all of the real numbers apart from 3, which is what we're writing down here, and that the range is all of the real numbers apart from 2. And again, you see the domain and range has switched around. Okay, now it says, and graphically determine whether this inverse is also a function. And they just want you to draw the graph here. Now, I think I did this one earlier, so here we go. Here's the two functions. The blue function is f to the minus 1 of x. You can see that it is a function, provided that we don't include, so let's just put in x is equal to 3. So x is equal to 3. The inverse function does not include 3, but it is a function as long as you take that, that value out. Okay, graphically determine whether the inverse is also a function. Yes, it is, as long as you don't include 3 in the domain. Okay, let's just see what they say in the book for that. I'm just kind of interested to see what they say. They say, yes, it is a function as its graph passes the vertical line test, therefore use the notation for inverse function. So it's okay to say this is f to the minus 1 of x. Okay. Well, that's kind of interesting given what we talked about in the previous exercise, because if we just based f to the minus 1 of x on the domain of f of x, then it wouldn't be a function. But here we're allowing, we're allowed to change this domain to say that x can't equal to 3 in this case. Okay. So, so there we go. Now I can see that the book has made a little mistake actually, in that, let's just copy this one. So the book has come up with a little mistake somewhere and it's working out. Let's go back to this and just copy it. And I think they've got the wrong function here. So let's just look at this. Yeah, and if you look at this, you can see there's the wrong function because they need to do minus 3 times minus 2 is equal to plus 6. When you take it to the other side, that gives us minus 5. So this should be minus 5. This should be minus 5 here as well. And that's what I had in my function, okay, 2x minus 5. Okay, so there's a little mistake in the book. That will be ironed out in all of the new versions of the book. This is just an original copy. I find it easier to use PDF sometimes. Okay, so right, what are we up to next? Yeah, okay. Let's look at the next one. They're talking about two functions are inverses in this box of each other. Their graphs have reflectional symmetry about y equals x. We talked about that earlier. So that's good. This, as another box here, it talks again about onto functions. It's good to recap on this. There's only functions that are one-to-one and onto functions have inverse functions. Remember, one-to-one means that for every number we put in, there is an answer, a unique answer, which is coming out. And onto functions mean to say that everything in the range comes from a number put into the domain. Okay, so every number from the range has been mapped from using this function. So in other words, we could say, for example, that this, if defined between here and here, I don't know, would maybe be the inverse function of this, that's reflected about y is equal to x, between those 2 points as well. What are we talking about? Saying that the original function has this main and this our range, and that every number in the range comes from a number on the x-axis, comes from a number in our domain, so that's onto, and every x value that you put in gives us a unique y value out. That's 1-to-1. Okay, right, that was defined in a previous exercise. So let's look at example 29. In fact, example 29, I think, goes through the same points which I was talking about earlier on. So it says, find the inverse relation of y equals x squared plus 1, and graph both the function and its inverse relation on the same set of axes. So this is pretty easy to do. You're getting that same, getting something like this. It's hard to draw, right? And something like this. And so there's your 1, there's your 1 in this case as well. Now, it says inverse relation, the relation because you're getting out two functions there. That's why they say relation and not functions. So the inverse function here is clearly x minus 1 all square rooted. So that's pretty straightforward. Now they say state two different domain restrictions of the function and the corresponding ranges. They're basically trying to get you to say, but this part matches up with this part, and this part matches up with this part here. So we've got our two functions there. So if we originally say, well, f of x is equal to x squared plus 1, then that's true only for the blue graph when x is greater than or equal to 0. And the range for that one is saying, well, y is greater than or equal to 1. By the way, you can make this more complete by saying y belongs to the real numbers. It's just following the condition. Okay, now y is greater than or equal to 1 because we're only getting out heights, which is greater than or equal to 1. So that's f of x, and f to the minus 1 of x under these conditions gives us the square root of x minus 1. So take away 1, square root is the undoing function. And you can see that that's giving you this, and the x values there are greater than or equal to 1. There's your 1. And the range of values which is coming out are greater than or equal to 0. Again, we can see the domain and range are flicking around. Now that's fine for the blue one. That's good for the blue set. Now, if we want to do the same thing for the green set, which is essentially what this question is asking us. Okay, state two different domain restrictions on the function. So the second domain restriction we can say is x is less than or equal to 0. So this is for the green part. And you can see there that we're also getting y is greater than or equal to 1. And for f to the minus 1 of x, you can see that the reflection here over y is equal to x is giving us the square root of x minus 1 with a minus in front. Okay, this is the negative of all of the blue heights. So that's true when x is greater than or equal to 1 still, but the range of that function is going to be underneath the x-axis. So in other words, when y is less than or equal to 0. Okay, so you're only getting out height less than or equal to 0. Actually, I think that answers both of these questions here. Okay, that's also done in the book. So you can see there's the relation which is drawn. So that's fine to draw the graph here, like I've drawn, but that constitutes two functions. So we have to split the original function into two one-to-one functions in order to come up with two inverse functions. Okay, the issue with the pink function or the magenta function that you see on the page there is that it's a many-to-one function. We need to split it into separate one-to-one functions in order to find their inverses. I think I've done that point to death now, so I'm going to leave that one. And finally, we're talking about self-inverse functions. Okay, so a classic one here would be to say, let's say if I do 5 divided by x, say for example, I do, I don't know, 5 divided by 10, that gives me 0.5 or a half. If I put 0.5 back into that function, 5 divided by 0.5, how many 0.5s are in 5? 10 of them. It's back to the original function. So this is a classic self-inverse function. All I'm doing is applying the same function again, and I'm getting back to the original function. Now they give this as the definition. They say, well, by the way, this function would be 5 over x. It's a reciprocal function. So 5 over x would be the same as its inverse function. All I need to do is apply it a second time. Okay, so that's saying that f to the minus 1 of x is equal to f of x. But I can apply that same function a second time and I will get back to the original answer. So what am I doing there actually? I'm doing f of, in this case, let's say 10. Okay, now f of 10 gave us out 0.5 and f of 0.5 gives us out 10. So we didn't need to use the inverse function, a different inverse function here. We're just using the same function again because it's a self-inverse. Now, also, it's true to say that f of x equaling to x means to say that f of x is a self-inverse. Okay, so that's another way of expressing the same thing. Okay, so if you find out that f of x takes you back to the identity function, then f of x is a self-inverse. That's exactly the same way of saying this thing here. Okay, so let's look at a question on this one. By the way, they talk about 1 over x. I've talked about 5 over x, but there we go. And oh, that's it. That's it. There's not a question for that. What I'll do is I'll just take this investigation here. Looking at this one earlier, it says determine whether, take this one here, determine whether functions of the form y equals x minus k over x minus 1 under these conditions here, x is not allowed to equal to 1, determine whether these are self-inverse for all values of k. Okay, nice question. Certainly could be an exam style question. So we're getting f of x, remember, is just equal to this thing here. So now we're going to use the technique, which is to switch x and y around in order to find the inverse. Y minus k and y minus 1. Let's multiply across by our denominator. And let's bring the y's together. We've got x minus xy minus y, x minus k there. Factorize the y Let's divide by that. So we're getting y is equal to x minus k over x minus 1. And there we go. We can see the function is the same as the original function. So we can say that this is both equal to f of x, and it's also equal to f minus 1 of x. Therefore, it is a self-inverse function. Okay, so that's pretty nice. I think we're done. Okay, well, thanks for listening to this one. We've got exercise 2N next. There's 5 questions there. And next we're coming on to function transformations, of which we've done quite a bit of work on this already just throughout these exercises so far. Okay, so well done on your efforts, and I'll see you later.